Welcome to this video presentation, Functional Coverage Simulation in VHDL. My name's David Clift and I'm an applications specialist for FirstEDA. FirstEDA is a value-added distributor of electronic design automation solutions in Northern Europe, specializing in software and hardware solutions for electronic design and verification. I'm joined again today by Jim Lewis, founder of SynthWorks, principal architect of the open source VHDL verification methodology, better known as OSVVM, and chair of the IEEE VHDL Standards Group. Welcome back, Jim.
Hi, David. Thanks for having me here.
That's a pleasure. As we discussed in our previous videos, FPGA designers today are facing the huge challenge of verifying their designs. Large or small, making sure they work correctly is an important part of the design task. And we're looking at how they complete that verification. In earlier videos, we saw about bus functional models, constrained random verification. And we learned that if you use constrained random, you need to know when you've tested everything. And one of the methods for doing that is functional coverage. In this session then, we'll look at functional coverage modeling. So Jim, how do I write a functional coverage model for my FPGA design?
Wow, that's a big question. So to address that, I've put together some topics to talk about here on functional coverage. Basically, we'll talk about types of coverage, classifying functional coverage, writing functional coverage, and then we'll take a look at constrained random and some issues with constrained random and how we solve them by randomizing across the coverage model, which is our intelligent coverage randomization. I also wanted to point out that functional coverage is just one piece of an effective verification methodology, which includes transactions, constrained random, self-checking, and error reporting. Okay, so when we talk about types of coverage, there's code coverage, which is a simulator collected metric on basically what code has been run. Code coverage clearly identifies what has not been run. However, it's optimistic because it's collected on delta cycles versus clock cycles, and in one given clock cycle, we can have many delta cycles. Okay, but we really only want to be collecting coverage at the last execution before the clock cycle, because that's the code that has effectively been run during this cycle. In addition, code coverage can only reason about things that are actually in the code. So if we leave something out, something in the test plan out of the code, then there's no way code coverage can tell us that that piece is missing. Functional coverage, on the other hand, is user-written code that observes the execution of the test plan. When a test plan has been completely executed, that's when our testing is actually done. So this functional coverage can be used to tell us test done, okay? And functional coverage ensures a test did what was intended, particularly when we're considering randomization, where we don't know exactly what the test is intended to do, but also for directed testing, as the test complexity grows, our test setup methodology, if there's any errors in that, it won't actually test what we think it tested, and our functional coverage will help us know that. So what I see as test done is 100% functional coverage, but I also like using the code coverage as a catch-all, as if I left something out of the functional coverage, the code coverage, if it's not run, will tell me that. So if we go further, we need to classify functional coverage, and we actually classify it into two different categories. One category is item coverage, which is also known in some languages as point coverage. Item coverage basically tracks relationships within a single object. So if we're looking at transfers, and we have transfer sizes from 1 to 255, so we might look for particular transfer sizes to have been executed in our testing. And when I'm thinking testing, I'm thinking boundary conditions, and boundary conditions usually happen at the endpoints. So as we get up to the bigger transfer sizes, 253, 254, 255, I want to see one of each of those. And as we get to the smaller transfer sizes, 1, 2, and 3, I want to see one of each of those. But when we get into the mid-range, 2 to 4 different bins, and I want to see a bunch within those within those group bins. Cross coverage is a metric that tracks relationships between different objects. Okay, so for example, if we're testing an ALU, the ALU has 2 inputs. Has each pair of registers or each set of registers that can be used with the inputs been selected with the other sets? Okay, so if we look at that exact example, we have an ALU. Each input to the ALU can select one of 8 different inputs. What we're looking for is, have we seen each and every register used with the other register? So we end up with basically a matrix of operations here. So we start writing the code. Basically, we start with a shared variable. The shared variable of cov p type becomes our coverage object, the object in which we're going to define our coverage model. And then to create our coverage model, we're going to call one method, add cross, and another subprogram, a function, genBin. GenBin basically takes that range 0 to 7 and breaks it out into individual bins. And then add cross crosses those sets of 8 individual bins with each other, so we end up with a matrix. We can test if it's all covered, so we basically loop until it is covered. And we're going to use simple uniform randomization here to do our randomization. And this is actually a very representative of what constrained random does, because each of these sources is independent of each other, so we'll randomize them separately. Then we'll do an operation, and we'll collect our coverage. Now, we're collecting our coverage perhaps in a different location than many languages advocate. And the reason we can do this here is we have to ensure that the do ALU op always does this. Always, when you say do source 1 and source 2, that it always only ever does source 1 and source 2. If do ALU op had some degree of freedom of what it was going to do, then we'd need to move the coverage to a place where we can actually monitor what was happening on the interface, or what actually happened on the interface. Okay, so one thing I want you to observe here is that functional coverage with OSVVM, it's basically as concise as any language syntax. In fact, I started the OSVVM project as, what should we do in the language? But then eventually I came to the realization is the answer to that question is nothing, because we can do as good a job as other languages have done with simply using a library of packages. Now, the other observation I've seen here, and this particular example illuminates it quite well, is constrained random ends up being slow. Okay? And the problem is constrained random uses uniform distributions. But what we want in testing is a small set of items. We want 1 or 2 of each test case. And to get 1 or 2 of each test case, randomization theory tells us it takes an order of n times natural log of n randomizations to generate those n unique test cases. So if we take a look at this particular example running with a particular seed, it took 315 test iterations. And 315 is approximately, just slightly less than, 5x too many iterations over the ideal 64 test cases. Okay, so what we've shown, though, is even for a small thing like this log n factor can significantly slow down constrained random tests. Okay. In fact, some of the intelligent test bench tools have done further studies that showed constrained random tests can take 10x to 100x off the ideal number of test cases. So it can be exceeding that by that multiplication factor there. Okay, so in OSVVM, we've created a methodology called intelligent coverage that's targeting generating n unique test cases in n randomizations. Okay, and basically the way we do this is we start by writing functional coverage. And then instead of randomizing using items from the randomization library we instead randomize across the functional coverage holes and take that information and use it to drive our stimulus and create our simulation. I'd love to be calling this coverage-driven randomization, but that term itself is actually used already by others to mean something quite different than this. So what do we need to do? Is it complicated to create an intelligent coverage randomization? Actually, it's simple. Okay? Instead of calling two separate randomizations, we're going to call this method that's part of the coverage model called RANCovPoint. RANCovPoint is going to return us an integer vector. And on the left-hand side here, we're assigning to an aggregate which breaks that integer vector into individual pieces, source 1 and source 2. And by the way, I only did that this way here because this example was already using individual signals. When we're working with the coverage model like this, it's more natural to use integer vector in these places. Okay, so the intelligent coverage methodology is step 1, write functional coverage. Step 2, do your primary randomization using the functional coverage model. And then, if necessary, refine that. Now, this example here does not show any refinement steps, but basically we would potentially apply algorithms to source 1 and source 2 to change their values at this point in the test bench. And by doing this, it also runs in exactly 64 iterations, which is approximately just slightly less than 5x faster than the constrained random example. Okay, so summarizing, functional coverage is important for any verification approach, and it's essential, particularly with randomization, to determine when test is done. In OSVVM, we've built on top of our functional coverage model and created this intelligent coverage methodology, which is basically, we call it intelligent coverage because it's basically an intelligent test bench methodology. And again, that methodology defines the functional coverage, we randomize across the coverage holes, and then we potentially refine with directed, algorithmic, file-based, or constrained random methods. And we can layer any of these because we're building directly on top of transaction test bench calls. The big takeaway is this. It's simple, it's powerful, and it's concise, and it replaces the need to add any additional syntax to the language.
Thank you, Jim. Very interesting, as always. And I think that rounds off the methodology quite nicely. We can drive random stimulus into our designs on the interfaces of those designs using constrained random stimulus and capture the coverage within the coverage model to ensure that we're actually testing to our test plan. So you know, it's a nice methodology. And on top of that, everything I've seen, it's standard VHDL. So it's not that much different to the RTL I'd be using in my FPGA design. So it seems that it's very easy for RTL designers to pick up the methodology and start writing powerful, comprehensive test environments to test their designs. So that's a double bonus.
Absolutely.
Okay, Jim. Well, thank you once again for spending time with us and joining us in this presentation. And I look forward to talking to you again soon.
Yeah, thanks again for having me here, David.
That's a pleasure. Thank you for joining us in this discussion and all the other discussions in this FPGA verification series.
If you're looking to get up to speed on functional coverage modeling and constrained random and all those methodologies, the fastest way to do this is our Advanced VHDL Test Bench and Verification class.
If you found it interesting and need more information, please visit our website at www.firsteda.com.